Welcome, welcome, welcome. So today we're going to be talking about the Pigeonhole Principle, and one of my favorite problems to introduce the Pigeonhole Principle is the Couriers Problem. So Professor Scarlet and Dr. Echo have been recruited by a general who wants to send a top secret message to a safe house behind enemy lines. So the general has 8 couriers that can be used to carry the message. However, there are 2 enemies that can each catch one of the couriers. So 8 of these try to get through, but it's possible that only 6 will get through. Now, to ensure that the message gets across, the general makes 3 copies and divides each copy into 5 parts. So we have 1, 2, 3, 4, 5 parts, and there's 3 copies. It's so secret that they won't even tell us what the parts are, but they did tell us that they've divided them up, and they'll call the first part A, and so on to the last part, they'll call it E. So the question is, how should we divide these 15 pieces among these couriers so that we can safely deliver this message to the safe house that's across the way? So our job is to take a look at these envelopes, divide up the message somehow among these 8 envelopes. So A's, B's, C's, and D's, and E's will somehow get fit in here. And there's 2 things that we have to make sure that when we're placing the letters in the envelopes, we have to make sure that the entire message will get to the safe house. And we also have to make sure that the enemy as a team doesn't get the whole message itself. So we cannot have the enemy getting A, B, C, D, E, and they will combine their knowledge. So we can't have one of the enemies getting ABC and the other enemy getting DE. So this is something that we can't have, and something that we must have is at least 1 copy of A, at least 1 copy of B, at least 1 copy of C, D, and E actually gets to the safe house. So pause the video now, see if you can make a distribution that works. There's more than one way to do this, but just play around with it and see what you can come up with. Okay, so as you're thinking through this, you may have noticed a couple things. So one thing to notice is that you can never put 4 parts on one courier. So we couldn't have A, B, C, and D on the first courier, because then there's one more E to send, but no matter where you put the E, no matter where you decide to send it, the enemy could capture the whole thing. The enemy could capture the first courier, and wherever they want, they could maybe find another E, wherever it might be. And we can't have those 2 get captured. So we can't have 4 different parts on the same courier. So this can't happen. So we'll erase what we thought of so far. Something else that you might notice that can't happen: we can't put the same part in the same courier. So we couldn't do something like A and A. Remember, we only have 3 A's in total. So wherever the other A is, let's say it's sent down here, what could happen is that the enemy could capture all of the A's. If all of the A's get captured, then we'll never get the safe house over here obtaining the whole message, because the enemy got all the A's. So we can't have this scenario. Okay, so let's erase those possibilities. We can't have the 2 A's together, or you couldn't have 2 B's together, and so on. You couldn't have 2 E's together. So what options does that leave us with? Well, we could have all of the A's separated. Maybe all the B's are separated, and all the C's are separated, and the D's are separated, and finally the E's are separated. And this would be a successful solution. The enemy, no matter what, can only capture a total of 4 parts on the enemy team. And that's not good enough, to get the whole message, because there's 5 parts in total. And each letter is separated in 3 different positions in our couriers. So each letter does indeed get through to the safe house, and we have a solution. Okay, so what does this have to do with the pigeonhole principle? Okay, so the pigeonhole principle says that if P pigeons each choose one of H pigeonholes to fly into, then we can tell something about one of the holes. Our discovery about one of the holes is that P divided by H, let's remember the ceiling function, it rounds that number up, that many pigeons, or possibly more pigeons, flew into one of the holes. Let's draw a picture. So I've just made up that we have 20 pigeons and they're flying into 9 holes. So these pigeons over here each choose one of the holes to fly into. And what we can say is that one of these holes, just picking one at random, we don't really know which one, we can say that it has the number of pigeons, which is 20, divided by the number of holes, which is 9. And the number has to be an integer, so we end up rounding this number up. So we get 3 out of that. That one hole has 3 or more pigeons. And we don't know it's that particular hole, we just know one of the holes. So what you can do with the pigeonhole principle is assign something in your problem to be pigeons and something in your problem to be holes. Let's return to the Couriers problem. At this time, we're going to reduce our number of couriers down to 7. We're going to try to find the minimum number of couriers. With 7, it will be a little bit harder, but the pigeonhole principle will help us get started. So we're going to let the pieces, the 15 pieces, the A's, B's, C's, D's, and E's, be the pigeons, and the couriers will be holes. And that makes sense because the letters needed to be assigned to the corresponding courier. Let's draw a picture just like before. So when our 15 pieces fly into our 7 different couriers, we can make a conclusion. One courier has 15 divided by 7 rounded up or more pieces. Okay, now in general, when you use the pigeonhole principle, you should always consider this or more part. These are pigeons, they're completely random. They could all shove themselves into the same hole if they like, but there's some additional information we know with this particular problem. With the pieces and the couriers, we know from the previous example that we did that we cannot have 4 pieces or parts on one courier. So this or more part can actually get crossed out just for this special scenario of this particular problem that we're doing the pigeonhole principle with. And the reason we can cross it out is by the note that we made on the previous page. So I think we called that note 1. Okay, so what we know moving forward is that 3 parts are on the same courier. So all the parts are symmetric. So let's just say A, B, C are sent on the same courier. That can give us some information about parts D and E. We can't put parts D and E together because if we do, then the enemy could capture the whole message. So if parts A, B, C are sent together, D and E must be sent apart. So D and E are not sent on the same courier. Let's put this to use and try to solve the problem with 7 couriers. So we were saying that, okay, A, B, and C will be sent together. As soon as we know that, then D and E must be apart from each other. So let's separate them out. So there's my 3 D's and 3 E's. And what's remaining to be sent is 2 more A's, B's, and C's. We can't put those A's, B's, and C's on the very first courier because that one's already full. 3 is the max, remember? But we can put them somewhere distributed anywhere on the other couriers, as long as we don't stick them together. We don't get any further restrictions. So the A's will get sent next, and the B's will get sent next, and then finally the C's will get sent next. So now the enemy cannot capture the whole message. If they need to get 5 parts, they'd have to take the first one and one of the other ones, but they would never be able to get A, B, C, and a D and an E. And all the letters are separated on at least 3 different couriers, so each letter gets through, and we have a successful solution. Okay, so we're searching for the minimum, and the last part of our problem here is to think about, well, if we have 6 couriers, does a solution still exist? Let's try to go through the same logic that we did before. Again, by the pigeonhole principle, we would now have 3 parts on one courier. And then again, parts D and E must be sent separately. So D's must be sent separately and E's must be sent separately. But now that final E that we still need to send, there's no place for it. It can't go with the D's, it needs to be separate from the E's, and it can't go with the A, B, and C because that would have 4 parts on one courier. Okay, so that tells us that the minimum number of couriers that we can solve this problem with is 7. Thanks so much for listening. We'll see you on the next one.